Our presentation this afternoon is about the Ferranti Atlas computer. Our speaker is committee member Professor Simon Lavington, who is a research student at Manchester and was fully involved in the development of Atlas when it was being developed there. He later moved to the University of Essex to become head of computer science. He's the author of several books of computer history and is one of the leading members of the society.
Thank you very much. This afternoon we got a rather tight agenda, I'm afraid, but you'll see that there's a gap for popcorn in the middle. I thought I'd start by just giving a bit of background to the UK's computing environment before what became known as supercomputers came along. Then talk about the National Research Development Corporation, NRDC, and their efforts to sponsor a British supercomputer. Then the Muse project at Manchester University, which became the Ferranti Atlas project, and the inauguration in December 1962 of that machine is what we've been celebrating just a few months ago. Then the light relief of the contemporary films, quite short, a few minutes each. Then the development of an Atlas II with Cambridge University. Then prospects for marketing, sales, the Atlas installations, how many, how do they come, and finally a bit of a reflection on what, if anything, remains as a legacy of those early days 50 years ago. So here we have the total number of UK commercially produced machines installed in the UK at the end of 1955, and there were a dozen of them, and a further 6 went abroad. The Leo, you will recall, is a one-off machine, but I've rightly included it in the list because it was a fully engineered, commercially active machine. So that was the UK situation. What were the prospects for, whoops, we seem to have gone on to, oh, never mind, there we are. On the horizon were machines like Mercury, the Ferranti Mercury. All the machines so far on the previous slide and on this one were single-user systems with, well, certainly the previous slide, no more than about a kilobyte of storage, and instruction times usually of the order of 1 millisecond each. The Ferranti Mercury came along a little bit later, a couple of years later, but was for some years the principal British designed scientific computer that was installed in some universities and in industry, and was, as it were, the star for a year or two of high performance computers in England. But still, I think you'll agree, a pedestrian design, single user. It had 1K words of ferrite core store, the cycle time of 10 microseconds, and I shall give some figures of its performance a little while later, but it was nowhere near up to the performance of the contemporary IBM machines, such as the IBM 704. Okay, so what was the prospects? This is actually the slide I thought was coming up just now. What were the prospects of further high-performance scientific computers? And I think it's right to say that the UK manufacturers at that stage, 1956, really lacked any vigorous ambitions compared with the Americans. The research groups were variously active. Cambridge was halfway through EDSAT-2 project, which had floating point hardware. NPL were halfway through finishing their full-scale ACE computer. Curious machine, no floating point hardware, delay line, Mercury delay line stores still. And I have to say, didn't quite make the impact on the computing scene that the Pilot Ace had. And Manchester University were kind of in limbo. They'd finished a computer prototype machine called MEG in 1954, which had floating point hardware, and that was operational within the university. The dynamics of the computer design group in Manchester were changing subtly. In the early years, the late 40s, etc., the lead figure, as far as the wide world was concerned, was F.C. Williams, Freddie Williams, and rightly so. Before the war, he was a high-flying academic. He'd got to a position of some influence as a designer of radar systems during the war, and after the war with the Manchester Computer Design Group, if anyone wanted somebody to sit on a committee from Manchester, it was F.C. Williams who was called for, not Tom Kilburn, his, as it were, his apprentice, you might say. But the dynamics were changing in the mid-50s when F.C. Williams started devoting his time to heavy machines, AC, variable speed AC drives, linear induction motors, and the way was kind of clear for Tom Kilburn to be more ambitious. F.C. Williams had been a little less ambitious with the design of MEG, and Tom was raring to go with something else, and so he started a project which he called Muse, a microsecond engine. The microsecond bit clearly putting a stake in the ground for an ambition to have speeds of the order of microseconds, which was you couldn't see the pulse edges on some of the oscilloscopes in those days, so it was rather, some people felt, far-fetched. At any rate, just one more slide about what Kilburn's ambitions were. Very much technology-driven, almost at the device stage, you might say. Like a lot of people, he saw the need for faster ALU and a faster and larger primary store. Interestingly, his group began to stretch their minds to how to handle large numbers of I/O devices, input-output equipment. The first thing they got working on was the parallel adders, and the sort of challenge of the age was to reduce the carrier time in parallel adders. And the group at Manchester went back to a basic relay type logic design where the switch is considered to be infinite resistance in one position and zero resistance in another. And the task was to find a suitable high frequency transistor that had those sort of properties. And in America, the Philco company were producing such a transistor, the SB240, at a huge cost. One of these transistors would cost you £30. And if you've got to multiply that by about 20 times to get the contemporary price today, you see that for a university group to try and attempt to build something with such a device was quite ambitious. But in due course, not obviously in 1956, but within a couple of years, they had produced something interesting in the speed line. With regard to storage, there were two thrusts being investigated. One was read-only memory, fixed store, for which a kind of tiny micro transformer configuration was proposed, where you had either strong or weak coupling in between primary and secondary, depending whether a little slug, a tiny pellet of material, was copper or ferrite. And the result eventually was a pretty rapid cycle time. With RAM, it was really down to the device physics level in conjunction with plastic, using various ferrite materials and small diameter cores, and developing partial flux switching with 2 cores per bit. Let's not worry about the detail, but if you see for the figure of cycle time eventually achieved, that 700 nanosecond cycle time at a time when the Ferranti Mercury was coming on the market with 10 microseconds cycle time. And interestingly enough, both those storage technologies were in the end limited by the characteristics of the drive transistor. Well, let's leave that Manchester group beavering away at a very low level and raise our sights to national and indeed international perspectives and imperatives. And it was certainly the nuclear lobby that was setting the pace for what was gradually being talked about as a supercomputer. In particular, the people from the UK Atomic Energy Authority expressed their need as a requirement to do about 10 to the 5th mesh operations per second, where a mesh operation on a 3D grid equated to about 10 machine instructions, one of which was a multiplication. So we're talking about a megaflop type of performance and a suitably large store. In the US, clearly it comes to no surprise to see that IBM was certainly rising to the challenge, and the Stretch project sponsored by Los Alamos, and for Univac's point of view, the LOC project sponsored by the Lawrence Livermore lab, were all beavering away, aiming to achieve that 1 megaflop per second. Compared with that, well, I've used the word hopeful, but really, perhaps I should say hopeless in terms of the British computer manufacturers' ambitions in those days, which were not terribly ambitious compared with the US. I've just given the end dates for the installation of Mercury, which we saw, and then a few more British computers, none of which achieved anything like a megaflop. We should also, rather curiously in my mind, include EMI as a hopeful on that list, for reasons that I'll explain shortly. EMI started to become a favourite of the National Research Development Corporation as the politics went on into the late 50s. Well, the UK's ambitions for a supercomputer, something to challenge the Americans, those ambitions were headed really by two players, obviously a potential user, the atomic energy people, and they divided really into the research and civil side and the weapons side, particularly Aldermaston. The National Research Development Corporation, you may recall, set up in 1949 with a capital of 5 million, with the Managing Director Lord Halsbury reporting to a board of directors, found itself occupied almost preeminently with pulling British computer designs into the marketplace. In the time that we're talking about, Lord Halsbury, who was a qualified and eminent scientist in his own right, and also one of the great and good, he had contacts hither and thither. He was ably assisted by Chris Strachey. I'm sure all of you have heard of Chris. And Chris, to my mind, became something of a personal technical advisor to Halsbury, as well as being a computer expert to NRDC itself. And NRDC, in its plans to promote a British supercomputer, clearly they sought advice from a number of people, not only the atomic energy people, but the Ministry of Supply, especially the Royal Radar Establishment, and the universities, especially Cambridge and Manchester. And so over the next couple of years, the NRDC tried a number of plans to pull through a British supercomputer. Plan A got nowhere. I won't bother to read the slide in detail, but this was to be essentially an NRDC design, purchased by the UK AEA, but that was not liked by the potential customer. Plan B was to consider the embryo project at Manchester, but that was rejected. Plan C, NRDC approached directly 3 British companies. English Electric rejected their overtures outright. EMI were very enthusiastic, and it may or may not have had something to do with the fact that the EMI's CEO was a board member of NRDC. And Ferranti hesitated, at that stage they hesitated. And NRDC was poised to support EMI. They changed their mind due, I think, to pressure from the main board, from which EMI person had resigned, and they decided in the end to put a little bit of money towards Ferranti and EMI. It's worth just recounting why the working party from NRDC turned its back on Manchester. Basically, the working party, which consisted of representatives from Cambridge, from the UK Atomic Energy Authority, etc., deemed that the storage and peripheral organisation was inadequate and that a fresh logical design was needed. Kilburn's response was typically direct and Yorkshire. He more or less told them to bugger off, basically. And at that stage he had a certain amount of funds. He had £50,000, which was savings from computer earnings internal to the Department of Electrical Engineering at Manchester. And he decided that unless he could design a machine in his own terms, he didn't want anything to do with NRDC. And actually, faced with that attitude, it's not surprising that NRDC says, sorry, we're not dealing with you. To summarise the eventual outcome, and we'll say more of this later on this afternoon, by the end of 1958, Ferranti, who had from time to time worked closely with the university, decided to come on board in a fully collaborative project with Manchester. The project's name was changed from Muse to Atlas. Ferranti obviously put a lot of money of its own into the endeavour. And you can see from these figures here the design team by 59 numbered 27, of whom 45% were academic and 55% were industrial. Before that, in the early days, there were 2 Ferranti people on loan to the university, but essentially it was a university project. As we've said, this saga ended with the first production version being unveiled in 1962, and Ferranti selling a few more, not very many, computers, and we'll deal with those sales later. So let's tell you a little bit about the story up until 1962, mostly in terms of pictures, and then we'll introduce a little bit of technology. There is a leaflet, booklet floating around, and if I appear to go too quickly through the technology, the facts and the figures are in this thing, and there are copies in the back. So, the photos. This rain-soaked building is the Department of Electrical Engineering at Manchester University, newly opened in 1954, and the computer group just occupied the top floor, and the rest of it was servos, machines, whatnot, all the other paraphernalia of electrical engineering. In sort of 1958 or so, prototype technology work was going on. Here is a chap called Dick Grimsdale, the principal designer of the read-only memory or fixed store, and you can see a mesh of they're little slugs like these, copper or ferrite slugs that go into a mesh within this frame here. This mesh comes from the production version. They weren't so prettily coloured in the prototype there. Dexian frames, everything was in a Dexian frame in these days. Right, there's an engineer called Mike Lanigan and Tom Kilburn with some prototype Muse circuits. Meanwhile, the collaboration with Ferranti was well underway, and Ferranti's printed circuit board production facilities at West Gorton were in full swing. And this photograph is about 1961, which shows lots of people assembling lots of things. And in one of the films that we see later on, we'll see a person assembling a printed circuit board in the West Gorton factory of Ferranti. On storage, well, this is the Fast B store. This stack lives inside this tank here, oil cooled, and these are the dry transistors. And in the film, we do see, if you as it were know what you're looking for, in the centre bay of a 3-bay cabinet, you can see a fan nestling in the back wiring, whose job was to frantically blow cold air at the dry transistors. This is a general purpose Atlas printed circuit board using germanium transistors, OC170s. This little fellow here is the special, rather expensive SB240 transistor that was put into the carry path of the parallel adder. There was no way that such transistors could be afforded for the main machine, and the parallel adder circuitry was a special. There were some 5,000 odd of these printed circuit boards in the total machine, of about 50 types in all. That's a picture of the pilot model of Atlas up in the top floor of the electrical engineering department in autumn 1960. And soon after the photograph was taken, the pilot model was moved to West Gorton, where it continued its existence for training and development purposes. Meanwhile, this area here was refurbished, false ceiling floor, false floor, etc., put in, ready for the production hardware. This shows the first production cabinet, 3-bay cabinet, arriving in the refurbished room of the previous slide. You can see the nice false floor there, etc. We shall see on film this cabinet arriving. The chap on the left is Alex Robinson, who afterwards headed up the London University Atlas installation. This chap is at that time a senior lecturer, Di Edwards. I'm afraid, I don't know the name of the technician, possibly a Ferranti technician. By the way, if any faces appear on these photos, and you, who I'm sure some of you worked on Atlas, if you can identify a face, do come and tell me afterwards, because that's one of these sort of anecdotal things, facts that I'm interested in gathering. That's the complete Manchester Atlas. This cabinet here contains the 8K worth of fixed store, clearly tape decks, 1-inch tape decks through there. A very cramped, a cramped layout. Here's the complete picture of the top floor of Dover Street, Electrical Engineering Department. At the time, the Ferranti Mercury computer occupied that space, and the whole of the Atlas installation had to be crammed into this space here. The 5 bays in reddish colour there are the main computer, and it's worth just identifying those bays, because later on I'll wish to say which of those units found a place within the Atlas II developments and which units were omitted from the Atlas II. In sort of the terminology that we would now recognise, these bays 7, 8, 9 are, I suppose you'd say, the central processor, the arithmetic units and control. More on that in a little bit. Brief introduction to Atlas from the programmer's point of view. A 48-bit word, not an unusual word length for those at that time. The 24 address bits, quite an unusually long address bit for the late 50s, early 60s. 10 bits for the function for the opcode. If the most significant function bit was a 0, then the bit pattern caused a direct execution in the traditional manner. If the top bit was a 1, then this was a call to extra codes, extensions to the autocodes, of which there are about 250, and they lived in the fixed read-only store. And apart from, as you would expect, routines, subroutines to aid the operating system and control the peripherals, there were extensions to user facilities, clearly trig functions and log functions, but also complex arithmetic, mixed radix arithmetic, etc. Over on the right, on the address side, if the most significant bit of these 24 bits was a 0, then that signified a user area, and the 20-bit virtual address, plus 3 bits to character level, was mapped by hardware into a block of real storage, the physical store consisting of Ferrite core store integrated with drum memory in what was at that stage known as a one-level store. If the most significant digit was a 1, then this indicated a private system area, and here there were 3 discernible separate physical devices. First of all, there was the fixed store, fast fixed store. Then there was what was collectively called the V-store, which was the collection of all registers and flip-flops throughout the machine to do with organisation, peripherals, interrupt, overflow indicators, etc. And then there was a modest amount, 1K words, of supervisor working store. And we can put all those bits of storage together in this following slide, where it's kind of colour-coded. Green equals storage. The haven't come out extraordinarily well. There's something wrong with your projector. These are meant to be light blue. Well, please imagine that they're light blue. The light blue things indicate processing ability, or these are autonomous control units. And then the orangey colour is the outside world, the conventional input-output devices pouring information in or taking it from here, and the tape decks. The address bus here to core store goes through via some page address registers, PARs, associatively accessed content addressable registers that try to find a match between a block of virtual storage, a page of virtual storage, and a block of real storage. And its common form is called a translation look-aside buffer, and you see them in all sorts of things, routers, etc. now. The job of this distributor was to work out clashes of priority. Atlas was an asynchronous machine, no clock, and for the first time, the synchronization problems between trying to synchronize independent events, these were coming to the fore in the hardware side. flip-flop settling times, etc. Interesting problems. The area of storage outlined by this squiggly green thing is the one-level store. The integration of drums and core store with the aid of the page address registers. Yeah, the one-level store. Because that's my nature as an engineer, I've tended to highlight hardware. There were some significant software endeavours that accompanied the hardware. First, the compiler. Tony Brooker, who was kind of the high-level language guru at Manchester at the time, his job was to design and implement a high-level language called an autocode in those days for Atlas. He'd implemented a Mark I autocode, a Mercury autocode. Now he was poised to implement an Atlas autocode. But this was at a time when Algol was being talked about. Committee meetings, reports, Algol 60. This inspired Tony to think more generally about languages and to produce a general tool based on BNF notation for describing high-level languages in general, and from this a tool for producing compilers for them. And this piece of software was known as the compiler, which had some influence beyond the Atlas project. Then there was Atlas Autocode. I think one of the reasons why Algol wasn't implemented at first on Atlas, apart from the difficulty of defining exactly what it was at that stage, Tony couldn't see how a one-pass compiler could be produced for Algol. So Atlas Autocode was an Algol-like language. And then finally, and most importantly, there was the operating system. And it's true to say that when the Muse Atlas team was getting going in 58, 59, 60 even, the task of providing system software was, it was not appreciated. Indeed, really, there was just one academic, Bruce Payne, to begin with, assigned to that task. So it was with most decidedly the effort of Ferranti, particularly David Howarth, that a small team that numbered more than 6 people implemented the Atlas Supervisor, which was a multitasking, multi-programming operating system of some 35,000 instructions. I won't go through this diagram of the supervisor in detail. It's in the book anyway, in the booklet. Basically, input comes in here via a number of peripherals, output goes down there, and the job of the scheduler here, an assembler, is to assemble a job list where each job could consist of up to 16 documents, and a document could be some program or a data set, etc. And the jobs ready to go were assembled in a well. The central executive part of the supervisor selected jobs for running, more than one job active at the same time, trying to balance the load on various pieces of equipment, particularly the tape decks. And then came the job of output assembly via an output well and final printing of results. So I'd like to pause now, and if we can get the technology to work, have 2 short films. If I tell you a little bit about them first, the first one, summer of 1961, so before the production version had all been put together, but the first bit of the production unit was in the process of being delivered to Manchester. The film opens with this rather wooden commentator's voice, and the visuals, the images, begin to suggest that Atlas is built of wood. You'll see what I mean when we come to it. But persevere, because this wooden voice commentator does say some reasonably intelligent things as the film goes on. The second film, which is a kind of newsreel snippet, if you like, the commentator is a jolly hockey sticks lady who, well, she doesn't truly understand the technology. And the most interesting part of the film, I think, she's on camera for the whole time. At one point, the camera swings into the corner where we see an embarrassed Tom Kilburn ducking out of the way and puffing on his pipe. And my guess is that the makers of the film had said to Tom, "You must appear in the film." And he says, "I don't want to do it," but they caught him with it on there. The other, to me, interesting thing about the film, towards, well, over halfway through, you'll hear a little blur on the soundtrack. And I've listened carefully to see what part of this jolly hockey sticks commentary has been obliterated. Because it seems clear, because we went back to the original film, that it's been obliterated by post-production, by somebody who said, she can't say that. And what she says is she's surprised that this computer was built at a university you've never even heard of. So, talk amongst yourselves for a little while, get out your bags of popcorn while I try and get these films going. Films start, there's a few seconds of just titles, and then the commentary, the wooden commentary begins.
An Atlas at Manchester. Using thousands of circuit packages like this, the world's fastest and most powerful computer takes shape, built at the Manchester computer factory of Ferranti Ltd, and destined for the computing machine laboratory of Manchester University. Long collaboration between Ferranti and the university has already produced the world's first commercially available computer, the Manchester Mark I, then Mercury, and now Atlas. Package shelves being assembled. Many parts of Atlas must be handmade, for automatic methods of construction are not exact enough to ensure the complete reliability that must be achieved if Atlas is to function as it should, with a speed and complexity that take current components and methods of construction to the limits of their possible performance. If only one part were to fail, the whole computer would be out of action, for with a computer, unlike other machines, there can be no operating at reduced efficiency. The circuits seen here being assembled and later interconnected represent great advances in design and were present in the forefront of world computer technology. Under the leadership of Professor Kilburn of Manchester University, new circuit techniques, including a new method of fast carry-digit propagation in the adding circuits, extremely rapid access to storage, and extensive parallel operation, have all been combined to give Atlas an operating speed of about 1 million commands a second, the fastest speed ever achieved. This speed is the limit of conventional components and methods of construction, because signals cannot travel faster than light, which only travels a foot in a millimicrosecond, and this is now a limiting factor in design as operating speeds increase. finished packages of many types, all using transistors instead of valves, and all carefully assembled on printed circuit laminates with hard-rolled contacts, varnished and tested, are the building bricks from which much of Atlas is made up. In the central bays of a computer, there are 1,200 of them. These bays form the central computer, and they contain the arithmetic unit, the control unit, and the index store. To make up a complete Atlas, many other bays, concerned both with computing and with power supplies, have to be added, together with a great variety of peripheral equipment, so that altogether an Atlas installation will occupy upwards of 2,000 square feet of floor space. However, Atlas is big and complex not to break a record, but to meet a demand. Current computers cannot cope with the work, great both in quantity and complexity, that needs to be done. But Atlas will provide about 1,000 times as much computing power as most medium-sized computers, and at a cost per computing operation that is less than on any other computer. First among the important design features of Atlas is the way in which the flow of information within the computer is organized in new ways to ensure maximum utilization of the computing power available. A supervisor program, permanently stored in the novel fixed store of Atlas, automatically controls the flow of work through the machine. Time sharing on Atlas enables any number of programs to be handled concurrently, and the supervisor program continually reviews the priority to be accorded to various jobs and allocates store capacity and peripheral equipment between them in such a manner that the most efficient working of the system as a whole is assured. The supervisor program also organizes transfers between various levels of storage, say from the drum store to the rapid access core store, entirely automatically, so that the user, when programming, need give no thought to the necessity for store transfers and may look on Atlas as having a single level store. The supervisor program also greatly simplifies the work of the Atlas operators by carrying out automatically all the scheduling of work being put on the machine. If programs and data are set up on any available input machine, the computer will find the ones it needs entirely automatically. Next, by providing several distinct paths of access to different parts of a high-speed core store, it has been possible for commands to overlap. In practice, this means that as many as 3 consecutive commands may be in different stages of execution at the same time. Lastly, many of the jobs which in other computers require extensive special circuits, for example to control associated punched card machines, are dealt with in Atlas by internal programs stored in the fixed store and obeyed by the main control unit of the computer itself, an advance only made possible by the very high computing speed of Atlas. The central bays of Atlas leave the factory for the university, where many departments and many organizations with problems in mathematics, physics, chemistry, biology, agriculture, economics, statistics, production planning, costing and engineering, problems that will take anything from a few seconds to a few hours of Atlas time, will use Atlas. Here, in the room at the university, where the first Manchester Mark I, 1,000 times slower than Atlas used to be. Following on the University Atlas will be other Atlases for other purchases. They will be programmed by hundreds of people, particularly if they are linked to remote users by data links. Programs for Atlas will arrive written in machine language, Mercury autocode, Nebula, and in other automatic programming languages. Atlas itself has been programmed to compile a compiler for any autocode. At the university, where Mercury is already in use by almost every department, Atlas will present immense new opportunities. It will be particularly used for nuclear research, for radio astronomy, for X-ray crystallography, and for linguistic analysis. Dr. Kilburn, responsible for Atlas design, seen here with some of the Atlas team, will also use the machine for further research in computing itself. The complete university installation will comprise computer bays, power supplies, 16,000 words of core store, 8,000 words of fixed store, 4 magnetic drums, 8 magnetic tape units, card and tape readers and punches, a hammer printer, and a graphical output plotter. in all making a system that will bring cheap, large-scale computing to a new world of computer users.
As far as I can determine, part 2 was never made. We haven't been able to trace it, and indeed it may have been the desire to produce a second film may have fallen foul of the ICT takeover, who knows. Anyway, let me see if I can fight the technology and get to the second film partner.
Hello there. Nolan Pritchard reporting from Britain. Ask me to name the one thing that's going to drastically change your life and mine in this century. And today, I can point right to it and answer this. It's a computer. There comes a point at which sheer speed of discovery can change our whole approach to understanding. And the computer opens up this new world. This one, named Atlas, just happens to be the latest, the fastest, and the most powerful in the world, that's all. What most computers today can do in 10 minutes, Atlas can do in 1 second. And as of this week, when Atlas comes into service, computer capability in Britain is doubled. There are only 3 types of machine that can even touch Atlas, and they're being built now in America and Japan, while even more Atlases are coming off the line here in Britain. Atlas doesn't just do better what other computers can already do. It can occupy it so fully in its spare time, automatically switching over to its homework if it happens to be too quick for its operator. It continually lets you know what it's working on and tells you if it's made a mistake. Atlas can do simple arithmetic at up to 1 million operations per second. Most impressive, there is already a demand for a machine with this capacity for work. This is not just for special, occasional jobs. Most computers now are swamped with work, and only something as big and fast as Atlas can tackle the kind of calculations now required for space research and atomic physics. Atlas will help the Meteorological Office study patterns of weather, and later it may even try its hand at weather forecasting. There are plans for Atlas to study French literature and analyze vocabulary. It may even do language translations. For all this, the computer is no equivalent to an electronic brain. More accurately, an electronic idiot by human standards, according to Professor Tom Kilburn of the University of Manchester. Incidentally, he designed the first computer made commercially available in 1951. You may ask, why build the world's fastest computer for use in a university you've hardly even heard? Professor Tom Kilburn happens to be here. And secondly, you just don't know the University of Manchester. It was here at Jodrell Bank the world's first radio telescope was built. When Russia's Sputniks went up in 1957, Manchester had the only facilities good enough to track them accurately. For a time, Russian scientists were almost commuting between Moscow and Manchester. And America's Project Mercury has made extensive use of the telescope. The new Atlas will soon be linked to the computer at Jodrell Bank. The Industrial Revolution began here in the north of England, and Manchester hasn't looked back since. It's an old saying that what they do in Manchester today, they'll be doing in London tomorrow. And it's true. The University of London doesn't get its Atlas for another 2 years. Nolan Pritchard saying goodbye for now from Manchester.
Right, to press on with something perhaps slightly less frivolous. In 1961, the University of Cambridge had certain needs and not enough resources to meet its ambitions for a very large computer. Fortunately, Peter Hall of Ferranti came to the rescue and proposed making available to Cambridge University certain Atlas hardware units, and with the accumulated Cambridge expertise in machine design and the joint efforts of Ferranti, producing a cheaper version of the Ferranti Atlas I, which the marketing people deemed was a necessary weapon for their campaigns. So that's what happened at Cambridge. The prototype was called Titan and is normally thought of as the prototype for a commercial version called Atlas II, of which 2 more were built. You will recall the list of component parts of the Manchester Atlas in a few slides ago. And in green on the right, I've shown what modifications were done in order to produce the slimmed down Atlas. And basically the main thing that was omitted was the mechanisms for the one-level store. Instead of having a combination of core and drum and the page address registers, the Titan prototype for Atlas had all core stores for its primary store, slower in cycle time, but as we'll see in a moment, more and more of it was added. And furthermore, the Cambridge academics designed 2 slave stores, 2 caches, to help with the access time. These were tunnel diode fast stores, one an instruction buffer, 32 lines, and one an operand buffer. I think it's true to say that the instruction buffer didn't quite work as desired, but certainly I understand the operand buffer was really useful. To cope with memory management along the data limit sort of philosophy, 4 extra registers were added. And this was the configuration upon which the joint Cambridge and Ferranti team worked in developing a supervisor for Atlas II. Partway through their endeavours, Maurice Wilkes, who had been visiting MIT at Cambridge, came back fired up with the desire to turn the Atlas II supervisor into a multi-access time-sharing system with users accessing the computer through terminals. And so in 65 to 66, a couple more registers were added, 16 million words of file disk, and multiplexer capable of handling 64 terminals. And in due course, I think first became operational to use this in 1967, the Titan multi-access time-sharing system came into being. Let's go straight into a discussion of what the outside world, apart from Manchester, saw all this work. What were the marketing opportunities? What were the hopes and fears of the Ferranti company as it tried to sell this rather expensive computer? Well, by rather expensive, I mean £2 to £3 million for an Atlas I, which is of the order of £50 million in today's money. This was at a time when Ferranti's computer department was under considerable pressure. They were developing another large machine called Orion at the same time, and it came to as no surprise to some when in the autumn of 1963, the Ferranti mainframe computer endeavours were taken up by ICT. Now, ICT had its own marketing priorities, largely oriented at the commercial data processing market, and furthermore, it had its upcoming new 1900 range of machines. So it's not surprising that perhaps not the most powerful marketing endeavours were devoted to trying to sell atlases. Thirdly, in this list of difficulties, was the fading technology. Well, this is true of all computers. New computers are like they're like watercolour paintings. They look marvellous in the first light of day, but as the light gets on and as time goes by, they fade. And so inevitably did the technology as transistor technology advanced beyond the germanium stage, and the gate delays. For example, a good fast gate delay in 1960 would be 20 nanoseconds. By the end of the 1960s, it was down to 2 nanoseconds. And of course, the US high-performance competitors, IBM and most especially CDC, took advantage of these technical improvements. The prospects were what you may suppose: the nuclear industry, universities, and establishments such as CSIRO in Australia, CERN, etc. What actually happened? Well, I put the word university in quotes here because of these three installations cited at universities, Manchester academics, by arrangement with Ferranti, only got half of the computing time on Manchester machine. The other half went to Ferranti's computing service. And with London, the difficulty, London had somewhat similar problems when it came to funding a large computer, as had the University of Cambridge. The University Grants Commission offered London a certain sum of money. I think it was 500k, which was not itself sufficient to buy an atlas. London cast around for an industrial partner, lighted upon BP, who put 500k into the pot in return for up to one shift out of 3 shifts of time. And finally, London University raised a loan for the rest of the 2 million cost. But it did mean that at London University, the installation, besides serving the academics, also had to earn money doing bureau work. At Cambridge, the situation was rather clearer, and as far as I can make out, the academics had full use of the machine. On the part of the nuclear people, by that time, it was more or less wall-to-wall IBMs at places like Risley and Aldermaston, but they did install an Atlas II at Aldermaston, and I'll say a little bit more about how that worked alongside Stretch. The biggest Atlas I installation came to a site variously called Nerns, Harwell or Chiltern. The history here is that just outside the wire of the Harwell Atomic Energy Authority labs, there was built another establishment called National Institute for Research into Nuclear Sciences, which is open access, open to university researchers, whereas Harwell was not. So the Atlas initially was called the Nerns Atlas because it was outside the Harwell wire. However, nobody understood what Nerns stood for, and everybody was familiar with the word Harwell, so that installation is often called the Harwell site. However, the twin villages of Harwell and Chiltern, their boundaries sort of span the physical place where the Atlas lab was set up. So, on the whole, now we prefer to call that site the Chiltern site. That was the biggest atlas. I'll give the figures in a moment. So this left one poor old Atlas II sitting on the flat factory floor at West Gorton, unloved and unsold. And it was mothballed for a number of months. I can't determine how many months, but say a year, 18 months even, until a sort of Prince Handsome came along in the form of Tony Benn with his white hot heater technology, his Ministry of Technology, funded, established a computer-aided design centre at Madingley Road in Cambridge and gobbled up the last Atlas II. So here's a checklist of the 3 Atlas I and 3 Atlas II installations. Well, it's quite clear that the Chiltern Atlas is the largest of the 3 large atlases. And it's interesting that I guess in the light perhaps of the falling costs of Core Store, the CAD Centre Core Store was the largest of those 3. The Atlas II installations. Now for some photos. I beg your pardon. I should not omit the attendant enthusiastic developments that are printed around each of the Atlas sites. Looking back, I think it was quite interesting that the presence of an Atlas seemed to inspire the locals, as it were. And one sign of this was the number of special I/O devices to be attached to each Atlas over the years, in addition to the normal data links to outlying stations. And these input-output devices are mostly in aid of improving the access of scientists, well, human beings, to the computers, particularly by the implementation of graphical input and output, and even speech input-output. A wealth of software was developed at these sites, and I've just picked out 1 or 2 for example. At London, there were a number of languages, including a commercial language and a survey analysis system. At Chiltern, where 85% of their users were academics, there was a need for a number of application packages for crystallography, etc. Also, Chiltern, being very close to the nuclear people, put great emphasis on the efficiency of Fortran, and the Hartran system, which as a subset contains the Aldermaston S3 Fortran compiler. They were what you might call shit-hot Fortran systems. We've mentioned at Cambridge the most interesting time-sharing operating system. At the CAD Centre, their task was to serve industry, and there were any number of applications packages, some of which are in use today, to do with, well, there we are, there's graphical design, plant design, numerical control tapes, etc., etc. There's a long list of them in the booklet, for example. The CAD Centre, which eventually was privatised, does exist today. Can't exactly remember the name of the company. It begins with A. It's rather like Aviva, but it's not Aviva. Very lively, and still using some of the packages developed at that time. What do these things look like physically? I've shown you 1 or 2 pictures of Manchester, which was a very cramped atlas. This is a scale model used by Ferranti and ICT as their salespeople travelled the world trying to flog these machines. And it shows a typical Atlas I installation on 2 floors. On the upper floor comes the mag tapes and I/O devices. On the lower floor come the logic cabinets, etc. And then not shown somewhere else come the motor alternator sets, the refrigeration, etc. This model incidentally exists today at the National Museums of Scotland in Edinburgh, and most of the units from the Chiltern Atlas are also in storage at Edinburgh. The top floor looks somewhat like this. Atlas could have up to 32 tape decks in 8 channels, and Harwell had, I think, Chiltern had about 16. And here we see a couple of line printers and the usual card readers, card bunches, paper tape readers, etc. A couple of half-inch IBM compatible tape decks for data interchange purposes. You might spot the TV camera and TV screen. Those are providing communication with the poor old duty engineer sitting all alone on the floor below, surrounded by these humming cabinets of the central processor. Atlas 2, I'd have liked to have shown you a picture of the Aldermaston installation. The nearest I can get comes from Ministry of Defence publication. It's very blurred, the photo, but you can see these units here are the same Potter 1-inch mag tapes that you see in this view of the Atlas 2 at Mintec. Also at Aldermaston was a Stretch. The only IBM Stretch computer to be installed in the UK was installed at Aldermaston. And looking at that photo and actually comparing the list of peripherals, which fortunately I've now obtained, it seems clear that the Stretch and Atlas 2 worked alongside each other for a number of years. Stretch was reserved for the production jobs, compute-bound production jobs, and the Atlas was used for program development and a sort of a workload of smaller jobs. And introducing a picture of Stretch leads me into the first of my sort of overview comments. How fast was Atlas? Well, we heard that jolly hockey sticks lady in the film talk about huge increases of power given by Atlas. Was that true or not? Well, we got some figures later that will address that question. Users, and Bob Hopgood, who I think is not present today, but is alive and well, I'm glad to say, was a Chiltern person who used both Stretch and Atlas, who developed programs for both of them, and his comments were that Atlas was, as a general purpose computer, was possibly faster than Stretch. I think the Atlas designers would lay out their stall not so much on grounds of raw speed, but on the ability to process work, throughput of a general workload. And this quote by Hugh Devenold, who was one of the leaders of the Ferranti's software teams, particularly I think he got involved in the Orion, he claims that if only you could have done a benchmark, and people really did, benchmarking was in its infancy in those days, but if you had two identical baskets of jobs, and you pushed one into the Atlas computer room and one into the Stretch computer room, Atlas's basket of jobs would complete before Stretch. And I think I think it's not appropriate to talk about the fastest computer at that time, but one might, with some justification, say that Atlas was, for a very brief period in history, perhaps only a few months, it could claim to be the most powerful computer. Here are some figures of speeds compared not just with Stretch, but with things like the Mercury. And you can see that I said right at the beginning of this lecture that Ferranti Mercury didn't really compare with the IBM 704 that was introduced 2 years before it, and you can see by these the floating point add times in microseconds how far behind Ferranti was at that stage. Rather than raw speeds, Chiltern came up with some overall factors, and they used these in determining, for example, how much time on Atlas to allocate researchers from a particular university who were applying for facilities on the Chiltern Atlas. It shows us their unit of speed Atlas, and that is 1, therefore, and they class it stretch as equal to that power. And you can see that Ferranti Mercury was down at 0.02. You can see why it became hard to sell Atlas, because by 64, when CDC had got to work, look at the factor that Chiltern assigned to that. I've just got a couple of graphs, so I won't spend too much time on them, but using Chiltern's factors, and Chiltern gathered factors over the 10 years period 59 to 69 for a number of machines. Before I do that, just let me reiterate this business of work throughput. You'll see that Bob Hopgood, when asked to really put Elliott's 803 computer in its place, claimed that you'd really need a lot of operators to keep a lot of Elliott 803s busy enough to match a week's work throughput. Well, I'm not sure, he's not here to justify that. What I was going to show is plotting Chiltern's figures year by year and dividing, excluding industry. We haven't got figures for industry accurately, but clearly Chiltern kept track of the Atomic Energy Authority's computing resource in terms of atlases, and that's the black line. It bumps along less than an atlas up until the point that atlases began to come into service, 63 or so, and by the end of that decade, you can see what I mean by the nuclear imperative. By that time, especially AWRE, wall-to-wall IBM, and far outstripping the computing resource, combined computing resources of all the universities. In particular, it's rather complicated lines, but the total UK universities computing resource before 62 was below 1, in the tenths of an atlas, all told, until the arrival of Atlas, when things started to happen. Perhaps it's clearer in the next slide. If you take just the computing resource available to all UK universities, which is the universities themselves, plus the usage they had of the Atlas Computing Lab at Chiltern, the total is this red line. And you see that the red line does take a step function of about 5 times, from 0.15 to 0.75. So in that very limited context, certainly Atlas made an impact. Well, what else? Do any of Atlas's innovations survive today? Well, some of the Atlas ideas, such as the carry path, the fast carry path, and the fixed store, they've sort of subsided into the primeval ooze of computer history. They were good at the time, but really, things have marched on by then. I possibly could have put the idea of extra codes in that list, but I didn't because I think one or two other manufacturers had extra codes in mind. I've chosen just 3 topics really, which I would say have had some influence, and indeed perhaps are still remembered by computer science practitioners as steps along the historical road. George Galoris from London University made that quote about the compiler. Brinch Hansen wrote a book in, I think, 2002 on classical operating systems, and seemed to think that the Atlas supervisor was significant. And here's a quote from Robin Kerr, who spent 5 years variously in university and then in Ferranti working on Atlas, and then afterwards went to work for CDC and then Schlumberger and one or two other American companies. He said recently that he felt virtual memory was perhaps the most significant thing to come out of Atlas. And I recently come across the word virtualization, and in the history of virtualization, which of course is wider than memory management, the Atlas developments seem to have a place. So that's it really. You'll find more information in that little booklet. And as a result of the small conference we had at Manchester in December, there is a website where there's a collection of papers, a growing collection of papers and anecdotes. And if any member of the audience has some personal recollections, some old diagrams, etc., we're still collecting. And either John Buckle, who is here, could you wave your hand, John? Either John or myself would be pleased to hear from you. Chiltern site has a lot of interesting documents, and of course there is the our computer heritage site. So that's it. Thank you very much.
Thank you very much, Simon. And does anybody have any questions or comments or contributions?
Do I gather that the logic technology was unchanged throughout the life of Atlas, still sticking with germanium transistors?
Yes. You see that the tape decks changed from Ampex to Potter. The drums, there's a big saga of the drums. The Ferranti drums proved lacking, and so Bryant drums were not. That's another story. But yes, the fundamental technology remained the same.
Good.
Well, apart from the tunnel diodes, of course, in the Cambridge.
You mentioned that some cabinets are still residing in a warehouse in Edinburgh. What would be the general outlook for a restoration?
Difficult. I'm not sure. I mean, I've seen the photographs, and there's cabinet after cabinet stacked up. There's a lot of gear up there. But whether it's come with the power supply switch gear and all that sort of thing, I doubt it really. But I tell you what would make, it would be of interest to at least extract a board from that parallel adder and have that on display. At Manchester we have got on display, or they have got on display, the pages rest registers, which are interesting because that's the first, there's no prototype for that. That is you would look at the first address translation unit. But in answer to your question, to regenerate Atlas, ooh.
Let's get that side done first.
A couple of first comments. First of all, you mentioned Iran several times.
Yes.
Something unfair. I would like to point out that Iran was trying to compete in a totally different market. It was deliberately made a slow machine for commercial data processing, and its actual throughput of data could be Atlas hands down any time, just the amount of stuff you could get through it. I was pointing out that 2/3 of the around development team sitting in this room at the moment. The other comment I'd like to make, in some ways, I think the successor of the Atlas machine was the Russian Bezin machine. Now, are there any comparative figures? Because once the Bezin was up and running, they got so hooked on it, there was so much software written for it, that it was still running Bezins in 2000 or so, because the software they had wouldn't run anything else. So the Bezin was in many ways a very successful machine. I suspect it was of the same sort of general concept of Atlas in many ways. I just wonder whether there are any comparative figures.
I haven't, but on that Bezin thing, they are to include significant amounts of Bezin hardware in the Science Museum's new exhibition. I do know that, but no, I can't tell you what the figures are.
So
that
makes 3 collections of computers. There is an after stuck away in Edinburgh, in a great heap, it can't be put. It's not actually put together. There's a stack of Orion somewhere in Birmingham, which is certainly never going to be put together, and there's a Bezin there, which also is never going to put together, maybe because all these manuals are written in Russian.
Just returning to your comment on Orion, you're quite right, Orion was for a different market.
It was a forerunner of 1900 in many ways.
Perceptions changed, didn't they? I mean, the attention to the commercial data processing market became more and more of a priority, and quite rightly so.
Sorry, there's Alan Wakefield. There are people better qualified than me in the audience to say this, but I think a lot of, you're talking about the heritage and the influence of that. Subsequently, I think a lot of design factors in Atlas influence a lot of the top-end ICT, then ICL development, top-end 1900 range, and particularly new range. Would that be true? I see Chris Burton nodding down there.
Well, it's certainly true that the Manchester Group
probably has agreed.
It's certainly true that the Manchester Group learnt a lot from Atlas, and I mean in the mid-60s we're doing lots of measurements on hit rates for proposed instruction buffers and things like that, and particularly this business of how many central registers should a machine have, and the answer seem to be 0, 1 or infinity. And Atlas's so-called lavish provision of 128 general purpose registers was not in the end thought to be a good thing. So I think a lot was learnt by the Manchester Group from Atlas, and as you know, the ME5 project, which was working in 1974, contributed to the ICL new range.
Sorry, this is just a detail, but I may have missed something. But what size of memory did the Atlas one have? Core memory.
Yes, the basic Manchester installation, which was the smallest of the 3, had 16K words of core store, backed by 96K words of drum store, where a word is 48 bits.
I'm more interested in the London Atlas.
Right, well, let me try and recover that slide, and you can see what's happening.
So I've been going around telling people for years that the London Atlas had 128K of memory.
Well,
I'm not quite sure, it depends whether...
No, I don't think quite. Let me see now whether I can pick up.
Maybe it was 128K 8-bit bytes or something. But we didn't think it 8.
I think this is the one I want. I have to say that those figures on the screen are how the sites settled down.
Yeah.
For example, as we said, they didn't have, none of the sites had, the early sites had file disks to start with.
So London Atlas had 123K. That was 48-bit words, is it?
Yes. Oh, it's 32. Yes, I can see there's a typo there. I do. Well spotted, sir. Well spotted, sir. Yes, that's 32K. Thank you. So the what happened next is interesting, because the computer board felt that they saw this image of large centralized computing facilities linked by data links, etc., to other sites, and people were looking ahead at some kind of formalized linking, and so the computer board created 3 national regional computing centres, one at Edinburgh, one at Manchester, and one at London. So when life didn't end in 1971, by 1972, the Manchester Regional Centre had a CDC 7600 front-ended by a 1906A. CDC was present in London University. So the whole thing exploded rapidly.
So,
there was a regional computing centre down in the University as well.
What did you say? Wasn't there? Yes, it wasn't. Yes, interesting. Yes, yeah.
Speak up.
without the microphone, we can't hear.
Okay. Well, the question was there anything other than the 3 main regional computing centres? And it was said that there was a consortium at Bath, Southwestern.
That was the Southwest University's Regional Computer Centre, which I moved from Umra, Manchester, to set up. So it was a proper regional centre.
Right.
The funding all went awry around that time for political reasons rather than anything else. It was in the original Flowers report that the regional centre should be in Edinburgh, Manchester, London, and the Southwest.
Ah, right, thank you.
It was more complicated than that.
David, life is a lot more complicated than any of us.
Because Cambridge was an IBM centre.
Pardon?
Cambridge was an IBM specific centre at the same time.
That's true, yeah. And Oxford piggybacked on the work to start with as well. So, yeah. Sorry, I was going to actually raise another point. I got a bit sidetracked there, Simon. Can I go back to the point I was hoping to make?
Please do.
Yeah, Jim Brooks, I did actually work on Ferranti Atlas in West Gorton and at the University of Manchester. Excellent presentation, Simon, thank you. I think early on you said there were 15 patents filed by Tom Kilburn and Co. I think I'm a bit concerned. Manchester modesty always gets in the way of how good Atlas really was and how fundamental it was in the long-term evolution of computing. Control data, IBM, digital, Honeywell, they're all bought into those patents and used a lot of the ideas behind Atlas. And there's one little story about what became the Honeywell 116, if I could just take a couple of seconds, because I think it's quite illustrative. I started in Manchester. I actually came back 10 years later to close Atlas down, so I had a long-term interest in the Manchester Atlas. But after being at Manchester for about a year, I got sent by Chris Wilson, who was the head of the Ferranti computing lot, to work on a small team in America to try and persuade the Americans to buy, not American, but British equipment, because we had the biggest ones, etc. I got invited to a session in MIT when Project Mac, which many of you may have heard of, was underway, and the audience was small, about 12, but quite distinguished. There was Professor Farno, Professor Cabato, who were the head of that, JCI Licklider, who was the director of DARPA, the Defence Advanced Research Project Agency. There was Leo Beranek, who was built Beranek and Newman, who, together with DARPA, produced ARPANET, which became the Internet. Marvin Minsky, the artificial intelligence guy, was there. John McCarthy, who produced Lisp, was in there. We had President Kennedy was still alive, and it was Kennedy's personal advisor in computing in the audience. So it was a small audience, and I was supposed to speak for about 3/4 of an hour. But I'd never been trained by Ferranti to speak publicly. It was my first ever public presentation. But I must have done something right, because in fact we went on for about 3 hours. And I thought naively, that we had a chance of bidding for the Project Mac, which has started off on the digital PDP-1, one of the early time sharing, 616. They wanted a big machine, and we got involved, and Frank Sumner from Tom Kilburn's team used to come over with me. We helped define the specs for them to go out to tender, and we thought, we're in here, good old Ferranti, we're going to get this business, because they more or less blueprinted a lot of the Atlas stuff into their formulation for Project Mac. Of course, what happened was they were picking our brains like mad, just took all the good ideas, put it in the spec, went out to tender, and the American General Electric company got the business and produced what became known as Multics. Now, that was eventually taken on by Honeywell as the Honeywell Multics. But a lot of the ideas that were behind there came out of the interaction between the Manchester team and the Atlas team. And it had a big influence. And I'm pretty sure that if someone did some proper research into how things evolved over the 60s and 70s, we'll find an awful lot of stuff that's come from a lot of that work that went on in Manchester originally. And that's just my view.
There's a question here.
Comment. So a couple of things work in reverse order. If you read Elliott's Organic Supercomputer Architecture, it answers precisely the last question, and it very much points out the Manchester contribution to virtual memory and how that went through to subsequent machines, including Multics. So it's a good read. If you want to see some bits of an Atlas II, there are a few cabinets in the Industrial Museum in Cambridge, and that would be one hell of a restoration project because you're missing all the interesting parts of the machine. Some bits did survive in Cambridge. This is a sneaky way of advertising a forthcoming talk here. 2 of the memory cabinets were used by CAP, and most of the power supplies got used in the Cambridge Ring project.
Thank you.
On the question, if you did refurbish these, sorry, just a question, if one did decide to get hold of these Edinburgh bits and put it all together again, what was the power consumption of a typical Atlas one? This is a question we have to address.
Yes, ponderous, I would say. I haven't got that figure on the top of my mind, but certainly you'd involve heavy-duty motor alternators. In Atlas, they trickle-charged a room full of batteries so that you had a clean power down in the event of some crisis. Yeah, well...
That would be insignificant compared to what Google have got on their server sites.
Yes, it's money consumption is the problem, actually, not power consumption.
Could you put your last slide on, please, Simon?
That one?
No, the one,
that
the very last one. Yep.
Yeah.
The top address there is the main Atlas 50 website, and from that you can get links to a number of papers that have been written, which are quite interesting. But you can also get a link to an Atlas blog site. The idea is that on the Atlas blog site you can comment on the papers, or you can add anecdotes which might be useful or interesting to other people. So far, apart from some tests, there are only 2 people who've contributed to the Atlas blog site, and one of those is me. Jim, if you don't put your story on there, I shall come round and personally wring it from you.
I should get the bottle of champagne out if you do, John.
Could I please ask anybody who has any anecdotes or technical information that they would like to register, please put it on there. It is very useful to people like Simon in the future, and other people will be interested. Thank you.
Thank you, John. Yes, very good.
Well, thank you very much indeed, Simon, and thank you too for your contributions and questions. So, thank you. And it's just been alluded to, but I would like to remind you that our next presentation will be on the Thursday the 16th of May, when Andrew Herbert will be talking about CAP. the last mainframe computer built by the Cambridge University Laboratory, and thus a descendant of EDSAC2 and Titan. Andrew worked on CAP as a research student and subsequently as a lecturer at Cambridge, and he's going to talk about the context in which CAP was designed, explore the novel aspects of its architecture, and show how its ideas have influenced more modern systems. Also, he will expose some of its very Cambridge quirks. On the human side, he's going to talk about the respective roles of Maurice Wilkes, David Wheeler, and Roger Needham in leading the CAP project. So I hope we'll see you there, here, next time.
Rachel, you've got the date one.
Have I?
Yes, it's April 18th.
Is it?
Yes.
April the 18th, thank you.
May 16th, which is the one after, is Doran Sway talking about Babbage's analytical engine.
Right, so we'll advertise that as well. So, thanks, Roger.
That's all right. April 16th, April 18th.